Module 1. Communication Fundamentals. Build the mental model. Let me slow this down and talk to you like an engineer to an engineer, because if you don't get this mentally, nothing downstream in instrumentation will ever feel fully solid. Before protocols, before PLC brands, before Ethernet, Fieldbus, Modbus, HART, or anything fashionable, communication mode is the very first engineering decision you are implicitly making. Most engineers wire first and think later. I want you to think first, like the signal itself. When two devices are connected, there are only three fundamental ways information can move between them. Everything you've ever worked with is just a dressed-up version of these basics. And the difference between a system that looks alive and one that is actually under control comes down to feedback. That's not a philosophical idea. That's physics and risk management. Simplex. One direction, no questions asked. In a simplex system, information flows only one way. Sender talks, receiver listens. That's it. On paper, it looks efficient. No contention, no timing issues, no coordination. But here's the industrial truth. Simplex systems are blind. The source material is blunt about this for a reason. In real instrumentation, simplex is of limited interest because there is no way to confirm that what you asked for actually happened to a plant floor mental picture. You have a pressure transmitter wired to a controller. The transmitter sends a value. The controller receives it. End of story. Now ask yourself, and I want you to really sit with this, what if the transmitter freezes? What if the wire breaks? What if the sensor saturates? The controller keeps listening, but nothing talks back to say, hey, I'm dead, or that value is no longer real. Simplex doesn't fail loudly. It fails quietly. That's why serious industrial systems don't trust it for control. Half-duplex. Taking turns staying honest. Now we step into the real industrial world. Half-duplex means both devices can talk, but only one at a time. This is not a limitation. This is a discipline. Most industrial physical layers, especially RS-485-based systems, live here by design. Only one station transmits, everyone else listens, then roles reverse. Protocols enforce order because chaos on a wire is far worse than waiting your turn. This is where feedback enters the picture properly. You send a request, the device responds, you verify the response. That round trip is everything. Half-duplex forces the system to ask, did the message arrive? Was it understood? Did the device act on it? This is why protocols like Modbus work reliably in harsh environments. The system isn't fast, but it's accountable. Half-duplex reflects how plants actually operate. One instruction at a time, one confirmation at a time, deterministic behavior over raw speed. You sacrifice simultaneity to gain trust, and in control systems, trust beats speed every single time. Full-duplex, simultaneous truth, higher cost. Full-duplex allows data to flow both ways at the same time. No waiting, no turn-taking. This is what engineers instinctively want because it feels powerful. Physically, this requires separate transmit and receive paths. Classic RS-232 supports this, and modern Ethernet takes it much further. But here's the key insight most people miss. Full duplex doesn't automatically make a system safer. It makes it faster and richer, but only if the higher layers are designed correctly. In instrumentation, full duplex shines when diagnostics are continuous, status updates are frequent, latency matters, systems are already well managed. Ethernet-based control systems thrive here because they assume robust error detection, retransmission mechanisms, layered protocol intelligence. Without those safeguards, full duplex just lets things go wrong faster. The PT-PLC reality check. This is where systems break. Now let's bring this home with the example you asked for. A pressure transmitter talking to a PLC. Imagine a world where communication is simplex only. The PT sends pressure. The PLC reads pressure. Now ask yourself, what breaks when the PLC can't talk back? It can't ask, are you alive? Are you calibrated? Are you in fault? Did you actually measure, or are you stuck? The PLC becomes a passive observer, not a controller. That's not control engineering. That's wishful thinking with wires. Half-duplex fixes this by enforcing dialogue. Full duplex enhances it by allowing monitoring and control to coexist in real time. And once you see that clearly, you'll never look at a simple signal the same way again. The mental model I want you to keep. Don't think in terms of what protocol should I use. Think like this instead. Simplex assumes reality is stable. Half-duplex verifies reality step by step. Full-duplex manages reality continuously. Instrumentation is not about moving numbers. It's about confirming truth under uncertainty. If you internalize that, every network, every wiring decision, every architecture choice you make from here on will start to feel obvious. And that's exactly where a good engineer should be. Synchronous versus asynchronous. Why Ethernet feels faster. Let's continue building the mental model, because this distinction quietly explains why some networks feel sluggish even when baud rates look fine, and why Ethernet feels smooth, confident, and effortless in comparison. I want you to forget speeds for a moment. Forget Mbps. Forget cable types. This is not about how fast bits move. This is about how receivers know when bits belong together. Timing is the real story here. When any device receives data, it faces a brutally simple problem. Open quote. How do I know where the data starts, where it ends, and how fast to read it? Close quote. There are only two fundamental answers to that question. Asynchronous communication. Characters with training wheels. Asynchronous communication treats each character as its own tiny event. Every byte says, "Hey, wake up, I'm starting now." That's what the start bit is doing. In asynchronous systems, the receiver does not share a clock with the transmitter. So instead of assuming timing, the transmitter explicitly signals it. Start bit, data bits, optional parity, stop bits, every single character. The source material lays this out clearly. The receiver doesn't even begin listening until it detects the start bit, which flips the voltage away from the idle state about the implication. Every byte resynchronizes timing, carries overhead, consumes dead space between characters. This is why asynchronous links feel stop-start in nature. They are polite, they are cautious, they are slow. Not because the wire is slow, but because the protocol keeps reintroducing itself. This is why classic RS-232 systems work reliably at low speeds and short distances, but feel painfully inefficient as data volume grows. Asynchronous systems are ideal when devices wake up sporadically, data is sparse, precision matters more than throughput differs. They trade efficiency for simplicity, synchronous communication. Once aligned, just flow. Now let's shift mental gears. Synchronous communication assumes something much bolder. Open quote. Once we agree on timing, let's just stream. Close quote. Instead of framing each character, synchronous systems frame entire messages. Before the real data begins, the transmitter sends a preamble, a known bit pattern that allows the receiver to lock onto timing. Once locked, the receiver no longer needs start bits for every byte. The tutorial describes this cleanly. Preamble for synchronization, start of frame delimiter, addressing, length, data, error checking. From that moment on, DS bits based on timing continuity, not voltage surprises. This changes everything. No repeated wake-ups, no per-character overhead, no guessing. Once synchronized, data flows like a river instead of dripping through a tap. That's why Ethernet feels fast, even before you account for bandwidth. Why this difference is felt, not just measured. Engineers often say, Ethernet is faster because it's 100 per or 1 gigabits. That's only half the truth. Ethernet feels faster because it synchronizes once, it streams continuously, it amortizes overhead across large frames. Asynchronous systems keep stopping to ask, are we aligned? Are we aligned? Are we aligned? Synchronous systems ask once, then move on. This is why high-speed LANs, Fieldbus backbones, and modern industrial Ethernet all rely on synchronous framing concepts. Bringing this back to instrumentation. Thinking now connect this to control systems. Asynchronous communication is character-based, perfect for simple commands, low data rates, point-to-point diagnostics. Synchronous communication is stream-based, essential for continuous measurements, high update rates, deterministic control traffic. And this is the line I want burned into your engineering intuition. Async is character-based, sync is stream-based. Once you internalize that, protocol choices stop feeling arbitrary. You'll feel why Ethernet belongs where it does. You'll sense why older serial links struggle under load. And you'll stop blaming hardware for problems that are really about timing philosophy. That's the kind of clarity that turns wiring into ASCII plus data coding. Why protocols exist at all. Now we go one level deeper, below wires, below timing, into something most engineers use every day but rarely pause to think about. Bits by themselves mean nothing. A voltage change is not information. A 1 or a 0 is not meaning. Meaning only appears when both ends agree on interpretation. That agreement is data coding. And this is where protocols are born. Let me put this plainly. When a device sends 010001, the receiver has to answer one question before anything else. Open quote, what does this pattern represent? Close quote, is it a number? Is it a letter? Is it a command? Is it noise? Without agreement, communication collapses into random electricity. Symbols before meaning. At the lowest level, communication systems don't transmit words or numbers. They transmit symbols, predefined bit patterns that stand in for meaning. Data coding is simply the rulebook that says, this pattern equals this symbol, that symbol equals this meaning. The tutorial makes this explicit. An agreed standard code allows the receiver to understand what the transmitter intended communication. Just voltage gymnastics. ASCII, the first widespread agreement. ASCII is one of the earliest and most influential coding agreements. It doesn't care about pressure, temperature, or flow. It cares about characters. Letters, numbers, punctuation, control characters. Each character is mapped to a unique bit pattern. For example, the letter D corresponds to the binary pattern 1000100. Now here's the key T-transmit meaning. It transmits symbols that humans recognize. That's why ASCII thrives in diagnostics, configuration messages, command-based protocols, human-readable interfaces. If you've ever typed a command into a terminal or read a Modbus register as text, ASCII was quietly doing its job. Why raw bits aren't enough in instrumentation? In industrial systems, we don't just ask, what character is this? We ask, is this a measurement? Is this a status? Is this an alarm? Is this configuration data? ASCII alone can't answer those questions. It can represent symbols, but not context. That's where protocols step in. Protocols, agreements with structure and consequences. A protocol is nothing more than a formalized agreement that says what symbols mean, where they appear, in what order, under what conditions, and how errors are handled. The OSI discussion in the tutorial highlights this beautifully. Wiring alone is not enough. Software structure is just as critical. These protocols don't exist to complicate life-end misunderstanding. They define. Framing, where messages start and end. Addressing, who is talking to whom. Semantics, what the data means. Error detection, when meaning is corrupted. Without protocols, devices may receive data correctly and still act incorrectly. That's the most dangerous failure mode in control systems. The instrumentation perspective. This is the real lesson. When a pressure transmitter sends a value, the PLC doesn't just see bits. It sees a numeric format, a scaling rule, a validity check, a status context. None of that exists in the wire. All of it exists in coding and protocol agreement. This is why two devices can share the same physical cable and still be completely incompatible. They don't disagree electrically. They disagree semantically. The mental model to lock in bits are physics. Symbols are agreements. Protocols are shared meaning. ASCII taught machines how to speak in human symbols. Industrial protocols taught machines how to speak truthfully about the physical world. Once you see that, protocols stop feeling like paperwork and start looking like what they really are. Contracts between machines that prevent dangerous assumptions. And in instrumentation, assumptions are where accidents begin. OSI model, and why industry quietly simplifies it. At this point, you and I are finally ready to talk about layers. Not as an academic diagram, but as a way engineers keep complexity from eating them alive. Because here's the uncomfortable truth. Real industrial systems would be impossible to build, debug, or maintain if everything lived in one mental bucket. So we slice the problem. Why the OSI model exists in the first place. The OSI model was never meant to be wiring instructions. It's a thinking framework. 7 layers, each answering a different question. How do bits move? How are errors detected? How are messages routed? How do applications talk? The tutorial frames it exactly this way. A structured collection of entities, each layer handling a clearly defined responsibility, powerful because it lets engineers change cables without rewriting software, change software without rewiring plants, isolate faults instead of guessing blindly. If something fails, you don't ask, what's wrong? You ask, which layer is lying to me? The full 7 layers. Elegant. but heavy. In its pure form, the OSI model defines 7 layers, from physical signals all the way up to application-level meaning. On paper, it's beautiful. In practice, industrial control doesn't need all that ceremony. Why? Because plants value determinism over flexibility, predictability over abstraction, fewer moving parts over elegant theory. The more layers you introduce, the more timing uncertainty you invite, and uncertainty is poison to control loops. Why instrumentation collapses the model? This is where industry makes a pragmatic decision. Instead of 7 layers, most instrumentation systems collapse the model into 3 functional layers. Physical layer, wires, voltages, connectors, data link layer, framing, error checking, who gets to talk. Application layer, the meaning of the data. The tutorial explicitly calls this out. Industrial systems often reduce the OSI model to these 3 layers to simplify operation and improve reliability. Everything else is IID'd. This is not laziness. This is engineering restraint. What gets gained by simplifying? By compressing layers, instrumentation systems gain faster decision paths, lower latency, easier troubleshooting, clear ownership of failures. When a transmitter misbehaves, you don't want to wonder whether the fault lives in a session layer you've never physically touched. You want to know, is the wire intact? Is the frame valid? Is the value meaningful? 3 layers answer those questions cleanly. The hidden extra layer, the one engineers actually care about. You probably noticed something subtle in the tutorial. Alongside the simplified OSI stack, there's mention of a user layer, not part of the official OSI model, but critical in industrial systems. This is where function blocks live, human intent meets machine behavior. This is why Fieldbus systems feel different from office networks. They're not just moving data, they're executing process intent. Why this matters before you touch a single wire? If you don't internalize this layering philosophy, troubleshooting becomes superstition. You'll reboot PLCs for wiring faults. You'll replace cables for configuration errors. You'll blame devices for protocol mismatches. Layered thinking prevents that. Once you can name the layer where a problem belongs, you stop panicking and start diagnosing. And that brings us exactly where we need to go next. Now that you can name the layers, let's touch the wires. Because the moment electrons hit copper, all these beautiful ideas meet reality, and that's where real instrumentation engineering begins.